So, hi everybody. It's good to be back on the conference circuit, at least a little bit, and appreciate the chance that we've got to actually come together, talk about some interesting stuff. Today, I'm going to be talking about some new work that's happening in the IETF. Part of it is work that's in the H2P working group. Part of it is work that's going to be that has been proposed but not adopted by the OAuth working group. And I wanted to take today to talk about kind of how these different specifications function, how the sort of the nuts and bolts of how they work, and how I think at least we can leverage them to do a lot of good work going forward. I think there's a lot of possibility here. It's a space that I see a lot of people asking about and have seen people asking about for many years now. And I think the tooling is finally getting to a place, the sort of prereqs are finally getting into a place where it really does make sense now. All right, so first off, a little bit of history. This whole idea of signing a request that has an access token in it and proving possession of an access token is not new at all. In OAuth 1, it was built into the protocol, but it was built in a weird way. OAuth 1 used query parameters and form parameters for everything, so it had its own method of normalizing and defining these query parameters so that you could sort of sort them together and sign them. And anybody who implemented OAuth 1 knows that it was messy and error prone, and everybody hated it pretty much. But you know, it worked for the security side of things. It just was not even close to being developer friendly. So in OAuth 2.0, bearer tokens were brought in as an option, even though they technically were in OAuth 1. It was kind of a weird fit. Bearer tokens came in in real force in OAuth 2, but this whole idea of a signed request didn't go away. Initially, we were going to be publishing the MAC token, which was really close to the OAuth 1.0 signature mechanism, and the bearer token in parallel with each other, due to lots of things that there's not nearly enough beer at 9 in the morning. This is water, I promise, to share that story right now. The MAC token spec ended up getting dropped, and that work kind of died on the vine. A few years later, the OAuth working group came up with the proof of possession architecture, which was going to be sort of a more sweeping grand approach to key distribution and binding to requests and key presentation and all of this other stuff in sort of a grand generic way inside of OAuth 2, the OAuth 2 framework. And part of that work was going to be how to sign an HTTP request. That led to a draft that I proposed and edited for a while called OAuth signed HTTP request. When I started work on that, I actually took a look at what was out there in the wild for HTTP, general purpose HTTP signing. And there were a few things, but nothing really quite fit OAuth's usage and use cases. For one, there was nothing that was in standards track at that point. And there were no RFCs or anything at that level of that caliber that would actually work for us. The stuff that was out there had limited coverage, was really inflexible in some really problematic ways. And so, being the young stupid engineer that I was, I thought, let's just make our own. How hard could that be? Turns out that it's really hard to sign an HTTP request. The way that the old draft in the OAuth group worked, which was its own custom signing mechanism, is that you take a bunch of headers, you mash those together, and you hash that, and you mash the query components together and hash that, and then you hash the body, And then you throw in a couple of extra variables for token values and timestamps and HTTP message components. And then you wrap everything up in a Jose web signature, and then you send that signature alongside the token itself. So there was a lot of moving parts around taking and normalizing different pieces of the HTTP message in their own little way, and then wrapping everything up in this Jose object just to chuck it across the wire. It kind of worked. I implemented it a few different times. It never really caught on, and the OAuth working group eventually kind of ran out of steam to try to even push this draft forward for a number of reasons, not least of which was the excitement that was growing around TLS token binding. May it rest in peace. Today, however, within the last year, we now have a new general purpose HTTP message signing draft that is an officially adopted document of the HTTP working group. Now, this is something that builds on several community drafts. And yes, I am one of the co-editors for this, along with Annabelle Bachman and Manu Sporting. This builds on the Cabbage signature draft, if any of you guys are familiar with that, which was an attempt to genericize the Amazon SigV4 work, which was their own proprietary signature method, which they still use to this day. The work, though, like once it really found a home in the HTTP working group, the IETF does what it does best and really, really picked apart the sort of the weird custom quirky bits to make this something that really fits well in the HTTP space. So we now have a draft. It's up to version 6 that works well with requests and responses, which is something that the OAuth draft never did, and the Cabbage draft was only so-so at. It works across all different method types and entity types. So there have been other approaches to say, like, take the message body and just put everything in the message inside a JWS and send that as your message body. It's the SOAP approach, but to message signing encryption, but with Jose. That only works if you have an entity body in your message, which of course you don't have in a GET request. And this also is designed to be a natively detached signature, so that all of the bits of the message that you're signing, it's very clear whether you're how to derive that portion of the signature from the HTTP message. But most importantly, it's designed to be profiled, and it's designed to be flexible in the ways that that security protocols like OAuth and GNAP need. So here we have a draft that tells you how to make signatures, but it doesn't tell you how to build that into your security application. It doesn't tell you what the signature means, who it represents. Doesn't even specify exactly which parts of the message you have to sign, because that is up to the application of the signature and the security profiles of it, such as you would use inside of OAuth. I'm also really happy to say that we finally have a playground that is available online. If you go to HTVsigorg, you can play around with signing and verifying requests and responses. It's probably a little buggy, but because we finally got it up on its new hosting environment last week, so we're still ironing a few things out, and it's a the playground is a shoestring project at best, but hopefully if you go poke around there, you can get a feel for kind of the different parts of the signing process, the different steps of it, and how it works. So I encourage you guys to do that. I can even do some live demo of that today if people are interested. So here's how the message signing draft works. This is completely separate from OAuth or any other kind of security protocol. This is just, you have an HTTP message and you want to sign it. So how do you do it? Well, first, you figure out which components of the message you want to sign. Are you signing some or all of the headers? Are you signing the method? Are you signing the request URI? What kinds of things are you doing? What keys are you going to sign it with? What algorithm are you going to use to sign it? You need to choose all of those going into the message signing. This is not something that's going to hand you all of those pieces and say, do this, do these bits. It is up to the application to decide what those parameters are. Then the next step, and this turns out to be one of the hardest parts, is normalizing all of those components that you decided to sign into a string, so that when you're doing a signing and you're doing a verification, you get the same string and therefore can validate the signature. Now, this is something that we've gotten a lot of feedback from the HTTP working group over the last year, how to do this. There are still pitfalls and caveats to any of this because HTTP, whether you realize this or not, is a very, very loose and very, very hand-wavy type of world. There's a lot of stuff that works in HTTP just because it kind of works that way. And so there's not a lot of structure to necessarily pull from. Next is the relatively straightforward part if you're working in any type of crypto space, and that is taking that string and signing it. And then finally, once you have that signature, the spec tells you how to attach that signature and all of the parameters you use to sign into a set of structured HTTP headers. Now, structured HTTP headers are one of the new building blocks that's made this work actually easier to build. They are a syntax RFC 8491 or 8941. Sorry, I always mix up those digits. It's a syntax for defining lists and dictionaries and strings and numbers and binary values and stuff like that inside of HTTP headers and trailer fields. And these items can be parameterized as well. But one of the things that's really, really good for us in a security specification is that it provides a deterministic serialization. So you can have relatively loose parsing input to a lot of these structures. So if you put something that's, that fits the dictionary syntax with extra spaces and all this other stuff, it'll parse into a dictionary. But when you serialize it, you can specify, use this specific serialization algorithm, which does not allow for any variability in terms of spaces or punctuation or anything like that. It is always done in one very specific way. It is also importantly a non-recursive algorithm, because when you get into general purpose data description like JSON, like YAML, like XML, you get recursive data structures and you get expansions of recursive data structures. So your objects can contain other objects, which can contain lists, which can contain other objects. And that's a beautiful thing when you're dealing with data representation. And it's a nightmare when you're trying to deal with things like security. Anybody that's tried to do a JSON LD signature or an XML DSIG will tell you what a pain that is to deal with. So this is non-recursive. The lowest that you can go is that dictionaries can have lists, an inner list, and a list can have one layer of inner list. The inner list cannot actually have anything else inside of it, and that's it. You can have parameters on things which act kind of like a dictionary, but those are not allowed to even have lists items in them, the inner list item. So we're not using JSON. We're not using anything like that. The other thing about this syntax, 8941, thank you, David. It's RFC 8941. David just, Skierberg, sorry, I'm butchering the name, just dropped the link into the chat. Thank you for that. One of the coolest things about HTTP structured header fields, though, is that it turns out that a lot of HTTP headers were already using a syntax or already complied with a syntax, but they weren't defining it in terms of one particular structure. It's just that People were using commas and spaces to separate values. People were using equal signs to separate keys and values. People were using quotes to wrap strings, double quotes. So there are a lot of HTTP fields that actually already fit this syntax, and the HTTP working group has proposed a retrofit draft to say, like, oh, all of these other fields can be effectively treated as structured fields. You can already do that. The way that it is used here in HTTP message signatures is that we use them for attaching things to the HTTP message, and we use them parts of that generation mechanism for the normalized message generation. So these are just some example structured fields that I threw in there. There's a lot more in the draft, and you'll see a lot more fields that are being defined by the HTTP working group are going to be defined as structured fields whenever that's possible. All right. So back to signatures. This is our example message. This is a really simple HTTP1 post. This signing mechanism actually also works against HTTP2 and HTTP3. I'm not going to go into the specifics of those details, but because of the way that we are defining all of the bits of the signing algorithm, it does actually work across all HTTP versions, which is another good thing that this new draft does that older drafts fell apart on. They relied too much on the quirks of HTTP 1.1. So we're going to decide that we're going to sign the method, this host field, the date, and the content type. I am arbitrarily picking these things for the sake of the example. The way that this comes across in the signature base is that we create a list of the things that we're going to sign. Each of these has what's called a component identifier. And we're going to use those component identifiers and the generation rules for those component identifiers to create our message. So first, we have the method. There's this @method identifier, and then we have a post. It is the HTTP method text string, which turns out, by the way, to be case sensitive. It's just something that surprised me when working on this spec. HTTP methods are case sensitive. I never knew. And then we have @authority, which we're pulling from the host field here, but HTTP2 and HTTP3 don't have a host header. They instead have a general authority control data field. So you could sign the host header, but it's actually recommended by the spec to use this @authority so that it is robust across different HTTP versions. Now we're signing the date header and the content type header here, just because, like I said, as an arbitrary example, we're signing those. The last thing that we add is the signature parameters. So all of these are being built up into a string. So we take the identifier, a colon, a single space, and then the value, and then a new line. We do that all the way down until we've got all of our covered elements. And then we take our signature parameters, which, as you can see, is not in this message anywhere. So our signature parameters is a list of the things that we're signing. These are all the component identifiers in an ordered list. This is using the HTTP structured field syntax and the deterministic serialization of that syntax. So we have method to match here, authority to match here, and then our headers, date, and content type. We can put these in any order that we want, but once we pick that order, the order is fixed. We now also have additional parameters that we're sending across with this example. We have a timestamp for when things are created. That's an epoch timestamp. And then we have a key identifier, right? This may or may not be a JWK key ID. It could just be a CN into a certificate if you want. The signature spec doesn't actually care, as long as you can interpret what that signature, what that key means. We take this string Oh, wait. So I should also mention that that signature params is always added as the last line in the signature base. The line break here is just for this for display purposes because it wrapped. But you take all of the things that you're going to sign, and then your signature parameters is always the last line of the signature base input, which includes the list of everything that you claim to have signed. So we put that through our signature algorithm, we get back a signature, and then we need to attach that to our HTTP message. We do this by adding two different headers. And the first is the signature input, which is the same as that last line that we had, right? At method, at authority, all of that. We name our signature and put it as a dictionary value into this header. And we do the same with the same signature label with the signature value, which is being sent as a binary label, binary value. Again, using HTTP structured fields. So one of the cool things here is that we can actually have multiple signatures that are attached to this message. So if I have different keys that I need to sign something with, if I have different targets for my signatures, and even if those sign different parts of the message, I can do all of that without them stepping on each other. So it's the basics of how HTTP signatures work. I'll actually pause for a sec if anybody has any questions about HTTP signatures before we start talking about OAuth. I know it's the first session. Everybody, especially our West Coast folks, are probably a little sleepy still. Reminiscent of DKIM, Travis, could you come? Would you mind jumping on the mic and saying why this reminds you of DKIM?
It reminds me of DKIM, Justin, and thanks for this explanation. It's been very good so far. In that you can have multiple signatures over it. You can pick what to sign arbitrarily, and then you just say what it is that you're signing. And also, the difference though being that standard HTTP header fields, that seems very good for making it so much easier to parse and to handle. So this seems great in my opinion.
Yeah, thanks. It uses that same type of say what you're going to sign and declare that methodology that DKIM uses, and I know a lot of other specs have taken a similar approach. OAuth 1 did, OpenID 1 and 2 did the same kind of thing. In a lot of other cases, though, this sort of last step of signing the list of things that you signed often gets lost. Which is one of the reasons that we are sending the signature input and the signature as separate structures in parallel with each other. But yeah, you're absolutely right that this is a targeted detached version type of signing mechanism. It doesn't encapsulate the message, but it also doesn't replicate parts of the message. So you see in my signature input, I say that I'm signing the method, but I don't say what the method is here. When you get the message on the other side, if that method is not the same, then the signature will fail by design. Which means that if you have reverse proxies that are doing funny things to different parts of your message, you need to take that into account when you're choosing which bits you need to sign. And the message signature spec is explicitly flexible about how you do that, but we also want to and are trying to provide a lot of guidance to people who are taking and implementing this with how you're doing that type of signature. All right, so how do we then take this and apply it into OAuth 2 or other security mechanisms? My proposal is that we have a new token type, the HTTP SIG token type, and we require to present the signature input, and authorization headers when you're using that token and sending it to the RS. This should also have a minimum set of message coverage requirements. Maybe we require that method and target URI get covered, for example, or I mean, obviously you would have to require the authorization header. Maybe there are other headers like content type or other things like that that you need to be able to sign for a particular application of this, and guidance for that and sort of a minimum set of that can be defined in this application spec. So what that basically means is we do the same process that we did before, and we just say, we've got this authorization header with our access token value, and we just add that into our signature. And then that goes in here, and we are, that's fundamentally, we're good. Because now the RS can take that token value and it can figure out what the token is for. And then it takes the signature value to figure out if the person presenting the token was supposed to be presenting the token with that message. There are some other features in HTTP-SIG that I didn't go into here. For example, if you want, you can in fact sign the individual query parameters if you want to get into that. You're not required to mess with those if you don't have to. You can just sign the URL as is if that's going to be stable for you, or you can sign the pieces of the URL. You can sign the body, but you have to use the digest mechanism to do that, which is a separate specification with its own header. So you calculate the digest, which turns to be its own really complex thing to get correct. So we're leveraging that work, and then you just simply sign the digest header and incorporate that into the request. I didn't do it in this example because I just didn't feel like calculating a digest here. Oh yes, I just talked about that. All right, so this is something that's a pretty simple application of a mechanism that is already out there. It is being implemented across a variety of things. So my thought was, let's apply this to OAuth. But of course, in the OAuth world, we have Depop, and Depop is going to be talked about today. My take on this from the beginning has been that they really should be able to coexist. If we can take Depop and really, really keep it minimal, like cover absolutely the bare minimum of things, have it really focused on this in-browser SPA use case. When you're using Jose and you're in an SPA, then you can do this, and you're doing asymmetric keys and all of this other stuff. Depop really flows very nicely. This specification comes with enough flexibility out of the box to do a lot more different use cases. Having clients that have pre-registered keys makes a lot more sense here than it does in Depop, which is targeted for SPAs, and therefore the key presentation mechanism and sort of that whole handshake and the key binding mechanism to the token are the same, which is a really, really nice simplification in the Depop space, but doesn't fit a bunch of different clients. Because say I want to have a pre-placed key inside my registration, I shouldn't have to send it at runtime, or I'm using certificates that are signed by a CA. Well, then, does that mean I need to send the CA cert every time that I'm doing this, or do I have to translate my certificate into a JWK, which is what Depop would require me to do? With this HTTP signature application, you could do a lot more different things without really bumping up the complexity. The complexity is already it's already a step that you have to take. It has not been optimized for any one singular case. My fear, and this is what I personally believe is happening right now, is that Depop is going to be taken and stretched very, very, very thin to cover a lot of different use cases and doing many of them awkwardly. And it's a case where it is a point solution, and in my opinion, it should not be stretched to cover all of these other spaces. We should have something more robust for all of those other cases. That doesn't mean we have to get rid of Depop, But I will say that if we had had HTTP message signatures and it was deployed and running and well understood 5 years ago, I don't think we would see, I don't think Depop would exist. I think we would have had something using this as a more targeted focused thing. We don't have that though. But I still think they should coexist. This does raise the question of why not actually just use Jose? So Depop does. The old HTTP signing spec from the OAuth working group that I had worked on uses Jose. There's a lot of good reasons to not use Jose. First of all, is that there are a lot of people in the world that aren't using Jose. And there's a not small contingent of the web that really dislikes Jose for a lot of good reasons and some misguided reasons. But the biggest reason for me is that Jose is amazing at self-contained cryptographic objects. It is one of the best systems that I have ever seen designed for doing that. And it is brilliant for tokens. It is brilliant for assertions. It is brilliant for so many different things. But when you're signing an HTTP message, you're no longer self-contained. You either need to duplicate or wrap portions of the HTTP message inside the Jose object. So if you want to cover headers, you need to hash them like the HTTP spec. If you want to cover the method or the target path or anything like that, you need to put them inside the JWS payload, which is what Depop does. Or you need to just take the very soapy approach and say, we're not actually really going to look at any of the outside HTTP message. We're going to just put everything that we want inside of the Jose object, and HTTP is just a dumb carrier for that. And those of you who lived through the whole WS star SOAP, enterprise architecture phase, will have some battle scars from dealing with systems that do exactly that. It's a premature abstraction at best, and a dangerous situation at worst, because all of the stuff that you've contained inside could contradict what's in the container, and that leads you to some really weird error cases. So those are the main reasons for not using Jose for the crypto mechanisms themselves. However, we do have text inside HTTP message signatures that says how to take a JWA algorithm and apply it to HTTP messages. So if I go back to this example, at some point, I need to take this string and turn it into a bunch of bytes. JWA tells me how to do that. It tells us how to do that in terms of Jose objects and Jose structures with Jose headers and stuff like that. But it turns out that there is enough flex in the language there. There's sort of a hook point in the language where we can say, take this string, this fully defined string, as the JWS input. You're not creating a Jose header. You're not encoding the body. You're not creating a JWS object out of the end of it. You are taking this as the JWS algorithm input, and that gives you a bunch of bytes that you can then use inside of HTTP messages. It's a really simple way to tie those two bits together if you're already doing JWA. And the demo code that I have on HTVsigorg, which you can also, there's a link on the bottom for the GitHub page if you want to see how it works. I've got this whole huge branch that says if you put in a JWK that has the alg field and it's a JWA algorithm, there's this branch that says like, okay, this maps to this crypto primitive, this one maps to this crypto primitive, and it just chunks it straight through without using all of the rest of Jose. So it's not using really JWS, it's not using JWS structures and things like that. It is just using those JWA definitions. So if you're already got a whole bunch of branching code that deals with JWA stuff, this is a really great way to do this. And so I've implemented it in a couple of different languages now, using Jose libraries for some of that heavy lifting. But there are also non-Jose algorithms out there that people want to be able to use for this stuff. So this gives us that kind of flexibility. Also, the advanced use cases of being able to do multiple signatures and chain signatures, so I can actually sign a signature that's already on a message, are very, very compelling, especially in today's modern sort of multi-tier architectures. So next steps, I've brought this to the OAuth working group a couple of times and it wasn't adopted. The working group said no. And the working group is working on Depop. But the spec is out there as an ID, which carries exactly 0 weight. But you guys can at least check it out. Myself and a couple of others are going to iterate on this a little bit. And hopefully this will eventually find a working group home, or be published as an independent draft. I'd much rather see it find a home in the OAuth working group, though. That's where this work really belongs. And it's my hope that this can take a lot of the pressure off of Depop. I'm seeing things added into Depop, which is really, really twisted around. There's the binding to refresh tokens and this Depop additional header that's being put in, and people trying to make it work with symmetric keys and all this other stuff. It's taking away, it's killing all of the stuff that a lot of us liked about Depop. And that's not fair to Depop. But it does mean that if this draft continues, HTTP signatures for OAuth, then we need to answer the questions of how do we deal with key distribution? Can the AS generate a key and hand it to me for my token? How do I discover that this feature is even available at a given AS or RS? How do I signal as a client that we need to be able to do this kind of thing? And then there's also an interesting question of how do we do client authentication using this, which is something that the MTLS draft did. Mike, you had your hand up. This is my last slide too, so at this point it's just discussion.
Finish your presentation, then I'll make a comment.
All right, great. And that's the end of my presentation. I'm not trolling you, Mike. That was literally the end. Go ahead.
Thank you, Justin. Gosh, it took you most of the hour to describe the HTTP signature mechanism. And it's really general, and there's a whole lot of choices, and it works across all the versions of HTTP. And, while I love the generality, this just confirms to me that the OAuth working group made the right decision to not use this mechanism. It seems way more complicated than even OAuth 1, which largely failed because it was too complicated and developers walked away from it. The HTTP signature mechanism, gosh, there's a lot of knobs and bells and whistles and custom code. Yeah, it'll eventually end up in libraries, but it fails what we in the OpenID Connect developer community jokingly, but not so jokingly, called the Nov Mataki test, where Nov, for those of you who don't know him, is a smart Ruby developer in Japan. And he was prone to, as we added a new thing to OpenID Connect, sit down for 2 or 3 hours, sometimes on a weekend, and just build it because he thought it was cool and it was easy to do. And if something was simple enough, Nov would build it and give us feedback. I can't imagine Nov sitting down and building HTTP signatures because there's just too much.
All right. Thanks for that. I will say that judging the length, judging the complexity by the length of a presentation that's specifically about that topic that I was introducing to this group, because I assumed that people weren't familiar with these specific mechanisms and would be interested in that, is misdirection at best and FUD at worst. I've implemented this a few times as we've gone through the various revisions, and quite honestly, the core is really not actually complicated. You've got headers and you sign those. The other bits you pull from the your message object. So like, you know, your message control data parameters, like your URL and all that other stuff. And at that point, it's string generation. So I don't think it's actually that complicated.
Well, it's a form of custom canonicalization, but and I do appreciate you explaining the mechanisms to people. I'll leave it at that. Thank you.
Thank you, Mike. Aaron, your hand's up.
Yeah, I just wanted to say one of the things I appreciate about this approach is the very hard separation between what is required to use this in OAuth versus what's actually happening under the hood. So what I mean by that is, like, the HTTP signature aspect of it has nothing to do with OAuth, which I think is correct. And it is its own thing, which means it can be built into libraries and it can be built in a way that people don't have to think about the OAuth side of it. And then actually applying it to OAuth, ideally, is actually very little code, because you would be, if you're not using a library, you would at least be interacting with code you've written at a different layer in just sort of choosing the fields kind of a way, right? Where it's like, you're not really doing canonicalization at that layer, at the OAuth layer, because it's all happening under the hood. So I like that separation of it. And I think that's a really good approach here.
Great, thank you. And also, I want to encourage people to go to HTVsigorg, and we've got a couple of minutes. Let me just do that real quick. All right. So go to HTVsigorg. You can follow along at home here, and you can see like how this stuff actually works. I'm seeing some stuff go by in the chat. Sorry, I'm not actually following everything. Let me do this first. The signing algorithm should be pre-agreed. So GNAP, yes, it's recommended by HTVsig that you pre-agree for security reasons. That's a security consideration, but there is a way to pass the information along as part of the message. It's one of the parameters on that signature inputs. And then there's a registry which says, this string goes to this specific crypto algorithm that uses these specific parameters. So you can pass it along if that works for your particular use case. Because of the potential problems in algorithm swapping that we especially see in the that we learned from years of dealing with Jose, that's not recommended. It's not currently considered best practice, but it is entirely possible, and I can show that in just a bit. You can also, another way to do that is that if you identify the key and your system is able to determine the correct algorithm based on the key material. So if you've got a JWK and it's in the alg field, or you've got a certificate and it's an HTTP PSS certificate, it's got all of those fields on it, you can just use that in your application as well. Okay, so HTTP signatures, here's how they work. I'm going to load up an example request. It's pretty close to the example that was actually in the thing. I'm going to bump my font size up too for you guys. First step is I'm going to take and parse this. I'm using just a generic HTTP message parser for this to get me all of my different parts. But here's the thing. If you are creating that message, you generally speaking have all of these parts available to you anyway. right? Because you know what method you're about to call, you know what URI you're about to call, you know what headers you're going to set. You have all of this available to you. So we are going to sign the method, the authority, and we'll do the path and query as well. You see, I can even sign the individual query parameters here. We'll also sign the content type field, and we'll sign the content dictionary. Actually, you know what? Just to do this, I'm going to sign just 2 parts of the structured dictionary field. This gets into what Mike was talking about as the bells and whistles, kind of the advanced stuff. If you don't have a need to sign this kind of stuff, you don't have to implement these bits, especially as a signer. As a verifier, you should. You should be able to handle this kind of stuff in case somebody sent it to you. But if your application is really only ever signing a couple of headers and a couple of message components, then don't go down all of the extra stuff. Demo. So that's our demo key identifier. I'm going to put a timestamp of right now, and I'm going to use that to generate my signature input. So we have @method, @authority, @path, content type, our different keys, and then our signature params has that whole list as its value with those additional fields added onto it. So now that we have our input string, we got to sign the thing. Here I can load, I've got some preloaded keys that I can use. I've also got them in X509 format. So we're going to do an ECC with an ECDSA. And we're just going to name it OSW just to show what's going on. And we're going to sign that. This is our raw signature, and these are the headers that we would add. George, question.
Yeah, so Depop allowed for, if I remember correctly, right, sending the public key in the assertion.
Correct.
Is there a way to do that with HTTPsig so that the downstream side can validate that the presenter has, in asymmetric keys, you're just looking to see, does this match, right? I mean, I could take the public key, I could have fingerprinted, I could look it up in my store to see if it's a client I trust or key I trust if I had to do that. But also it might just be, yes, I know the presenter of this message is in possession of the appropriate private key.
That is not so key distribution and agreement is not a problem that HTTP message signatures tries to solve, and that's a very deliberate decision. It's that hard line that Aaron was talking about, but it's something that applications of this could solve, and it's something that the OAuth application of this really ought to solve. The easiest way to do it is really something similar to the original Depop proof, where there was like a Depop JWK header field, and then you chuck your JWK into that field, which let's go get one. You got me curious. I want to do this end to end now. So we've got our public key, and then the spec. But yeah, we just do something like this. We put it into HTTP header format, which doesn't do well with JSON, but we can make it work. And as long as that works, where is it? We sign that, and I'm gonna just sign that for now. So see, we've got our input string there. And the important thing is we don't send the input string across the wire, unlike Jose, which is self-contained. The input string is generated by the verifier, and there's some verification functions on this page that you guys can play with too. So we are seeing libraries of this starting to get implemented. People that have been using the Cabbage signatures for years across like the 12 different variants that all kind of broke something different are starting to dig into this this a little bit. So HTTP message signatures are going to happen whether the OAuth group working group likes it or not. That part's not up for debate. It fits a very, very real space. The question that I brought to the OAuth working group, and I continue to ask the wider community, is, does it make sense to take this thing that exists and apply it to OAuth? And I think it's dumb not to, but that's my take on it.
Justin, I have another question, if I may, but I don't seem to be able to raise my hand. So in the chat, I asked if the request that you're signing has an authorization header, and you get a signature that's produced by that, and you use it as an authorization header, you'll have duplicates and some HTTP headers. Okay, how would that work?
The signature. Okay, so the signature does not go in the authorization header. This was one of the problems with the Cabbage spec, is that it overloaded the authorization header. For this spec, we are explicitly defining our own header spaces, and we are not using the authorization header.
I thought in the example it said authorization and then HTTP-SIG and then the token.
That is the token value. That is not the signature value.
I see. But still, it's an authorization HTTP request header, right?
Yes.
And so if you had another one in there, how would you put both of them? Because some HTTP headers you can have multiple of, but some you can't.
Yeah, authorization you can't.
Okay.
If I recall correctly from the ABNF. But doing the process of signing does not add an authorization header.
Okay. Didn't you have that in your sample on the slides?
That was not added by the signature. Here, let me go back to the slides. Here, give me a sec to switch back. All right. So the way to look at this, you know what? Just let's do it this way. The way that it actually starts is this. Okay.
Okay.
All right. So this is our unsigned request. I didn't change the title. We already have a token that's been handed to us. This is our access token. We now need to take this message and sign it. And that's where we add these bits to it. So tell you what, let's just go and we will just straight up drop this into the playground. Oh, for crying out loud. Thank you, Microsoft. Mike's on the call. Can you get the Office team to fix this? This is annoying. Or if somebody from Mozilla, we can blame Firefox. All right. All right. So this is the message that I'm signing. And I'm going to say, I want to sign the authorization header, the method, and the target URI. I'm just going to leave everything else off for now. We'll use all the same stuff. This is my signature input. We'll use the same key and crypto parameters that we had before. And that gives us these two things, right? These two headers. So what we end up with is this is our final message here. So the input message has an authorization header. That's where the token lives. And we're adding the signature to that message that already has the authorization header. We are not adding an authorization header.
Okay, so it could have been bare, and this could have been an access token from some authorization server or something, as you call the resource server, but you're just changing the token or the the token type.
Yeah, the token type is to signal to the RS that it needs to look for, this is not just a bearer. It's not good enough to just see the token value, but the token value is completely separate from the security presentation side of things.
I got it. It looks great to me. I think I mentioned also in the chat that Depop suffers from clock synchronization between client and server. That's very difficult in large deployments. And this doesn't seem to have that, plus being able to arbitrarily sign any part of the message. I think this makes this superior to Depop.
Thank you. People are asking, what was the technical reason for not considering HTVsig? That's up to the OAuth working group, and I'm not going to get into that. I see 2 hands up. Dimitri.
Yeah, thanks for the presentation. And do we actually define a mechanism to bind an access token to the key, similar to CNF/JKT section claim for Depop?
Yeah, that's what the OAuth draft would do. I think I put that here. No, I didn't do that in the strawman, but yeah, we would. That's what we would need to do. There would be a CNF section inside the token itself or in the introspection response. The other question is, of course, how do you stand that up? Unlike Depop, this was not meant to. HTTP message signatures doesn't solve any of that. The OAuth with HTTP message signatures would have to, in some combination, solve that. Right? Another hand up. It doesn't say your name, unfortunately.
All right, Philip here. Hey, just in very quickly, I'm amazed by how quickly HTTP signatures have progressed. So good job, love it. Now
Annabelle's done a lot of work too. Got to give her credit.
Right. So I hear a lot of like at the being thrown at Depop for adding things that do not feel at home in that space, in that spec. Most notably the recent nonces that were added. That being said, if HTTP signatures were profiled to replace Depop, God forbid replace, but do the same thing as Depop does, wouldn't it suffer from the same clock synchronization and the same nonce and being able to pre-compute signatures and all of that? Just like Depop does. I mean, after all, you have a date inside the request and so on and so forth. I know it's harder to pull off, but I feel like the same problems would have to be solved somehow.
So I didn't show it in the demo, but there is a nonce parameter that you can add to the signature inputs. So it goes like right here, kind of thing. So there is a signer provided nonce. Anything that would be server provided would need a higher level protocol to do that nonce negotiation. Pre-computed inputs really come down to how much of the message you sign. So if I decide, if I want to be super dumb and not sign anything, then that's what my signature input looks like. And that could be used for literally any HTTP message. We've got a lot of security considerations talking about why that's a bad idea, but that's the kind of thing you could actually do. And so all of those are possibilities in HTTP signatures. It's just that's not the specific bit that was needing to solve.
Right. Likewise, I can put a random nonce inside the Depop proof myself as well. And if I choose to sign the date, it's like putting IAT inside the token only. On the HTTP wire, I don't get to choose the date that, or maybe I do, I don't know.
Yeah, well, that's why we've got the created parameter that's separate from the date header, and there's security consideration discussing that as well. That's a known oddity. We've got very little time, Brian. I just want to make sure we grab you before we go.
Yeah, I don't know that I have much more to add from what Philip said, but some of those, there's a lot of shade being thrown at Depop because it adds those things based on specific needs and requirements coming out of the working group. And while they're not a part of what you presented here, they're also not addressed in it. So things like a server provided nonce around freshments, time restrictions on acceptance of the message, they don't go away just because they're not discussed. They're still relevant here. You still have the same issues. They just haven't been worked through in the draft. So I don't think there's a bit of unfairness in the comparison at this level, because what we've got here is moving complexity into the HTTP signature layer, which is nice, and ignoring some of the other complexity because it hasn't been addressed yet. So it's not a straight up comparison.
I did not intend it to be a straight up comparison. They should not be directly compared.
I know, but it's coming across that way in the comments and the discussion.
Gotcha. Apologies for that. Yeah, it's not a direct comparison because Depop, like I've been trying to say this whole time, it takes the approach of solving everything end to end in terms of key binding and presentation, and associating that with the token during all of the requests and stuff like that. All of that happens in kind of one specific arc, one specific way. Those are other questions that would need to be answered. Even if you take out all of the signing mechanism portion of Depop, the other bits could still potentially be used, which is what I was showing to George, if the OAuth working group wanted to do all of that. My comment about complexity, though, I'm going to stand on that, though. I do think that Depop is getting stretched in ways that I don't think it ought to be. I don't think it's going to be good for it. And it's starting to feel a little token binding-y again. But we will leave that there. All right, thank you, everybody. Great discussion.
Thank you, Jeff.